Here I would like to introduce our first speaker and keynote speaker, Professor David Morens from National Institute of Health from the United States of America. Professor David Morens is advisor to the director of NIH, and he also worked with the US CDC as the chief of respiratory and special pathogens branch. So I'm really looking forward to his great story about lessons learned. And here's to pass the microphone to Professor Morens. Floor is yours, please.
Thank you, Nikki, and hello to everybody out there. Yes, I'm going to talk about a century-old pandemic, but this is not a history lesson. What I hope to do is talk a little bit about how sepsis and septic shock and death from bacterial disease comes about. And this is to talk about natural history and pathogenesis. And one of the points to be thinking about as I speak is that if sepsis and septic shock and death are the downstream events, what are the upstream events and how do they progress? Because if we can answer that question, we'll have some ideas about what we can do to prevent the outcomes from happening. So let's go back in time more than 100 years ago, before the 1918 pandemic of influenza, and talk about something that is relevant to everything else I'm going to say, and that is the subject of bacterial viral copathogenesis. People being infected by two different microorganisms at once, one a virus and one a bacterium. The realization of the importance of copathogenesis came about in the early days of the 20th century when immigrants were coming into Ellis Island in the United States, and health officers there began to realize that children infected with measles and other viral diseases, but I'm speaking of measles most particularly, had a certain mortality rate. But if they were co-infected with other things like streptococci or diphtheria, their mortality rate was much higher. This was an epidemiologic observation. A few years later, the United States entered World War I in 1917, the third year of the war, and there were a number of Army training camps set up, which had a total population at a time as much as 1 million soldiers at a time, and there were outbreaks of everything, including a massive measles outbreak, which ended up killing 3,206 soldiers. And these soldiers died not of measles, but of secondary bacterial pneumonia. One study, which is a particularly good study, cohorted soldiers that came in with measles. So what they did is this. Every soldier who presented with measles had a throat culture taken for group A beta hemolytic strep Pyogenes, or then it was called strep hemolyticus. And soldiers who had a positive culture were sent to one particular ward to be isolated for their measles. And soldiers who had negative cultures went to another ward and were recultured every day. And what they found was that of the complications and deaths, 100% of those were in soldiers who were colonized with strep. Now, nobody died of streptococcal disease per se. They died of secondary bacterial pneumonia, and streptococci was found in their lungs. And the pneumonia pattern was bronchopneumonia, and bronchopneumonia is a pattern in which the lesions, at least in the beginning of the process, are around the bronchial tree, and I'll talk a little bit more about how that happens. So now we're coming to measles, and now we're coming to influenza, not measles. I think as most people know, the measles epidemic in 1918 was the single most fatal event in the history of the world. 50 to 100 million people died. In our laboratory here at NIH, one of our laboratories here at NIH, we obtained from the Armed Forces Institute of Pathology specimens from 58 soldiers who died in 1918 from influenza, and recut and stained them and looked at them and found that 100% of these 58 autopsy slides showed that death was associated with severe bacterial pneumonia. We also did a literature search of the era of 1918 and early 1919, and we found every article we could find in 15 countries in multiple languages, 173 studies reporting autopsy results on over 8,000 people, soldiers and civilians, all of these having both pathology results and bacteriology results. And what we found was that in 95% of cases, there were pneumopathogens cultured from the lungs at autopsy. By pneumopathogens, I mean bacteria that are normally or are sometimes found in the upper respiratory tract of normal people, but which have the ability to cause severe pneumonia. So 95% of those autopsies in soldiers and civilians that had pleural effusions, and the pleural effusions were cultured, 80.4% had these pneumopathogens. And significantly, of the people who died and who had blood cultures obtained before death, 70% had one or more positive blood culture. And the pneumopathogens I mentioned were particularly three: strep pneumoniae, which is pneumococcus, strep pyogenes, or group A beta hemolytic strep, and staphylococcus. But there were others as well. There were actually outbreaks in which fatal pneumonia associated with 1918 flu was caused by meningococcus, that is, meningococcal pneumonia. And those soldiers did not die of meningococcal meningitis or even meningococcemia. They died of meningococcal pneumonia. So what are the lesions close up that are associated with these copathogenic infections? The viral lesions are fairly constant, and that is the infection of apical cells with bronchiolar and bronchial respiratory epithelium. You can think of it as we know that the bronchial tract is lined with protective cells, epithelial cells, and there are goblet cells and mucin-secreting cells and ciliated cells that protect the respiratory tract from anything going down. And these are the things that are destroyed. It's kind of like mowing the lawn. When the virus comes in, it mows the lawn. It strips away one cell layer thick of epithelium, and then other bad things can happen. So the 1918 pneumonias were almost all bronchopneumonias, just as we saw a minute ago, or I said a minute ago, in talking about measles pneumonia. There were bronchopneumonias, and almost all of them were associated with massive infection. But evidence of tissue repair was there. So the virus did its thing, but it repaired quickly. And one would imagine that had these people not got secondary bacterial infections, they would have been fine. They would have recovered, just like most of us recover from influenza. It's worth asking here, what was the proximate cause of death? These people died of bacterial pneumonia, but that's something that would be written on the death certificate. But how actually did they die? It's a little hard to tell from clinical notes written long before we had ICUs and the types of studies we can do now, like oxygen tension and so on. But it appears to me, at least, from reading many, many of these autopsies and clinical reports, that the causes of death were often from damage to the, from hypoxia that resulted from either damage to the pulmonary tissue, there was just no more gas exchange, or else from alveolar edema. The alveoli actually were filled with water. Sometimes death appeared to result from sepsis and septic shock, presumably associated with multi-organ failure. And in some cases, not very often, death was due to heart failure or renal failure apart from multi-organ failure or from late complications. So by 1918, around the world, pathologists understood that this copathogenesis was what was killing people, the virus plus bacteria. A French physician said, if grippe or influenza condemns, the secondary infections execute. And the preeminent pathologist of the 1918 pandemic, William McCallum, a Canadian-American, essentially said that he had never performed an autopsy of somebody who died of flu in which he didn't find bacteria. So just to sum up what I've said about measles and flu, there's these two pandemics in the military camps that were studied, and one was 1917 measles, the other was 1918 flu. 100% of all U.S. Army camps were involved. The deaths were large, the case fatality rate was large, the bacteria that caused the deaths were largely the same, and the pathology, with a minor exception or two, the pathology of measles pneumonia deaths and flu pneumonia deaths were identical. This was essentially the same disease. And McCallum noted that it appears there were two great epidemic outbreaks of pneumonia, the first closely associated with measles, the second following influenza. In other words, he didn't think of these as epidemics of measles and influenza. He thought of them as epidemics of severe bacterial pneumonia, which just happened to be set off by the two prevailing viruses of that era. Now, it's not possible, of course, from an autopsy to look at natural history and pathogenesis because the person died only at one point in time. But when autopsies are done, you can look at the tissues and find the lung tissue, for example, in different areas of the lung or in different stages of the process. And by doing enough of these, you can develop a sort of a picture of the progression, the natural history of the disease as it evolved, even though you're only seeing the snapshot, not the whole movie. And when you combine that with epidemiologic data, here's what seems to have happened. In both of these epidemics of measles and of influenza in army camps, there were colonization, what I would call colonization epidemics of bacterial pneumopathogens. These soldiers come into camps, they're in crowded barrack conditions. There are epidemics in which everybody becomes, almost everybody becomes colonized with strep, or if it's a different situation with pneumococcus. And then a cytolytic virus comes along, a virus that mows the lawn of the respiratory epithelium and may go all the way down the respiratory tree. There are the defenders against bacteria going out of the nose and throat and down into the lungs are gone. The defense is gone. The bacteria go down and adhere to the denuded, the basal layer under the denuded epithelial cells, set up bacterial pneumonia, and this is what explains the pattern of bronchopneumonia as opposed to lobar pneumonia. And by the way, the same sort of patterns are seen in flu deaths today. So now fast forward a little bit to the modern era where we have experimental techniques, and many researchers, including some at NIH, have begun to study viral bacterial co-pathogenesis in experimental models, usually mice, not a very good model, but it's easy, also in primates, and I'm going to discuss a little bit about that. In many mouse models and many laboratories, if you give an influenza virus, for example, the 1918 virus or others, plus a bacterium like pneumococcus, the pathology is much worse. And that's true, and the death, the rapidity of death and the total death of the experimental animals is much higher when some viruses, at least, and influenza viruses we're speaking of now, and some bacteria at least cause disease together or are given together. And it's the same thing, the same story I mentioned before that was put together from natural history reasoning about the 1918 pandemic a century ago. In viral infection alone, the epithelial cells are gone, but the basal cells remain. In co-pathogenesis, the bacteria come in and destroy the basal cells, and now the bacteria have access to the parenchymal tissue, and they can spread out unimpeded or largely unimpeded by the defense mechanisms of the host. So, some things we can say about studies done here and elsewhere are that that influenza infections increases bacterial replication if the bacteria get there, and that this results in severe necrotizing bronchiolitis and alveolitis with also suppurative pleuritis. Also, and I'll show this in a minute, I'll discuss it in a minute, there's marked neutrophil activation, at least with the 1918 virus, and increased reactive oxygen species, and cell death and elastase deposition, as well as activation of the extrinsic pathway and thrombosis. Now, there's a large body of experimental work on this, I did, a few years ago, I looked at how many papers had been published studying influenza bacterial co-pathogenesis in a 3-year period, and it was 252 publications. By now, it's many hundreds of publications. So many labs are working on this. It's a big topic of research. And I want to also mention, this is a little bit of an aside, but one of the things learned from this, from these animal studies was something that clinicians predicted was true 100 years ago in 1918, that pneumococcal transmission between experimental animals occurs at a higher rate, or only in some experiments, when the animals are infected with influenza as well. That is, influenza infection also not only is a setup for more severe disease and bacterial co-infection, it causes transmission of bacterial disease. So we're beginning to see a pathogenic model of what's happening, and it begins with the widespread viral epithelial injury caused by the virus, influenza in the case I'm talking about. An inflammatory response occurs. In the case of the 1918 influenza, uniquely, that inflammatory response involves recruitment of an enormous number of neutrophils. In some other influenza viruses, most other ones that have been studied don't do that. This viral damage leads to increased bacterial invasion and adhesion and higher replication or higher colony amounts of bacteria. Damage to the tissue results in decreased blood flow. There's an immune response to the virus and to the bacterium. The viral immune response is involved in activating even more neutrophils, even in the case of other viruses, not the 1918 virus. And the bacteria induces its own immune response. And the downstream cascade of this is that neutrophils, and in some cases macrophage, release factor 3, which cause increased platelet activation, elastase, which causes thrombus formation, and the result of this is increasing tissue damage from the combined effects of the infection of the two organisms and the damaging immune responses to both of them. So I'm going to end by just giving you some thoughts to ponder about, and these are my thoughts, they're not experimental research thoughts. But given a couple things that I'm going to mention, that influenza and other respiratory diseases like RSV and parainfluenza are so common and they're not likely to be prevented in the near future. We have no vaccines, for example, and they cause significant mortality. And given that colonization of the upper respiratory tract with these bugs of interest, pneumococcus, strep and staph, and others, is very common and not likely to be entirely prevented in the near future. In most viral epidemics, only a small percentage of people have these severe complications, but when they do have it, the time from the recognition of the complication, by which I mean developing bacterial bronchopneumonia, to the time of severe disease or death, is often very short, sometimes a matter of hours. So that suggests that if we're going to intervene with antibiotics, there's probably, in many cases, a really very narrow window of time in which antibiotics must be given, and after that time, they may not work. Therefore, I think there's an urgent need to identify patients with impending complications and perhaps, hopefully, identify and use early biomarkers of bacterial bronchopneumonia, perhaps based on bacterial genes or proteins, host response genes, or systemic inflammation markers. We also need to understand more about the natural history and pathogenesis. But in the meantime, we do have influenza and pneumococcal vaccines. They're not entirely perfect vaccines, but there's mounting evidence that they do reduce death. In some cases, don't do a good job of preventing disease, but when disease occurs, they do reduce death. And I think, in addition, we need to make sure that healthcare providers counsel patients at risk, the elderly and those with chronic diseases who are most likely to die from influenza, RSV, and all these other viral diseases, and have a plan for them to get seen on an emergent basis when a complication might develop. Thank you.
Thank you, Professor Morens. There is one comment from German participants that saying that we still have a high mortality rate from influenza in Germany annually from 10 to 12,000. And this is a comment from the participants. And it is very likely that it is the combination of virus and bacterial infection that kills these patients. We would like to welcome more questions. While waiting for other questions, I'd like to pose some questions to you, Professor Morens. So it will be ideal if we could have these biomarkers, especially if they are available as point of care diagnosis. But the World Health Organization has to be better prepared for the next pandemic. If the situation is such that the mortality is very high, and if we are to see the same pattern like 1918, then would you recommend the early use of antibiotics, antimicrobials, to treat influenza infection? Over to you.
Okay, thank you. Well, it's a good question and one I've thought a lot about. I guess I'd have to say that the evidence isn't quite there yet, in my mind, to make a clinical recommendation of treating patients before they have a problem with antibiotics, and that entails problems of its own. It's something that perhaps should be a decision individualized by clinicians, and there might be several aspects of that. One is give everybody antibiotics when there's a flu epidemic. I don't think anybody is going to vote for that. Another might be just give antibiotics to people who are at high risk who have influenza, but even, not complicated, but uncomplicated influenza. The problem with that is that even in 1918, the case fatality rate was under 1% probably. So that whenever you give, you can't, the problem is we can't predict of all the people who get influenza, which ones of those are going to go on to get a bacterial complication. Even elderly people who are the group at high risk, the vast majority of those people get influenza and they'll do fine. So I'm really not answering your question, but saying it would be an easier question to answer if we had a way to predict early on who was, coming down with a serious complication. And, there are some of the work I presented a minute ago that is from studies in which host response genes have been looked at in animals, experimental animals. And it's becoming clear that the host immune response pattern to influenza bacterial co-infection is relatively specific for some viruses, such that if you had a way to detect that pattern, F3, high F3 release or something like that, it might be possible to someday have a test that shows that people are or are very likely to be developing bronchopneumonia, even though their chest x-rays will be fine and it may be afebrile.
Thank you. And then I remember the famous W-shaped mortality curve during the 1918 pandemic. And then the mortality was highest in younger populations, such as the population represented by young soldiers. So are there any immunological or specific reasons why these populations are more affected and have more complication, like secondary bacterial or co-bacterial infection? Over to you.
Yeah, it's an interesting question. I think that there's a lot of theories, but most of them don't seem to hold water. And I don't think there's any plausible theory other than the theory that the rate was not necessarily higher in young adults. It was lower in people over that age range because of immunity to a previous virus in the 1800s. Now, that's a theory that fits all the facts, except if it's true, that means that without that protective immunity, the case fatality rate would have been extraordinarily higher in people over 40, something we've never seen with any influenza virus before. So I think the returns aren't in. But it's interesting to note that the reason that all these people died, remember that the peak is not the peak age in the W in 1918, which was the people who were in that peak were roughly age 20 to 40 or something like that, 25 to 45 in that age range. Those people who died didn't die of influenza. They died of bacterial pneumonia, just like everybody else. So we have to think of it as, why did so many people die of bacterial pneumonia? And their case fatality from bacterial pneumonia was no different than it was at other times. In other words, they had a higher rate of bacterial pneumonia, but they didn't have a higher rate of dying from bacterial pneumonia than people in 1916 and 1913 and other years who had the same types of bacterial pneumonias. Complicated problem.
Thank you very much. It's a great talk.